Good morning, this is Dr. Turner for Integrated Math 2. Today we're going to be talking about 8.3, which is looking at segment relationships in circles. Now, I will be the first to admit that as we go into Unit 8 and we get through 8.1 through 8.5, there's a lot of vocabulary that you want to be familiar with. We talked about the different definitions of terms that we haven't come across in 8.1 and 8.2 so far. So 8.3 might be a little bit confusing. If you haven't watched that video yet, you might want to go and take down the definition of these different line segments because a lot of these are going to be similar looking. So if you're not sure, I would go back and get those definitions down. Usually I'll kind of sketch as I'm going through on my little pad here, but I went ahead and just drew the diagrams so it'd be a little bit easier and the video would go a little bit quicker. So with that, let's go ahead and get started. Today we're going to be covering 3 theorems involving the segments of lines that are going through a circle. Those segments are our chords, our secants, and our tangents. So we have 3 different relationships that we're going to talk about here. The first is chord-chord. Second is going to be secant-secant. And the third is going to be secant-tangent. Just as a brief reminder, remember that a chord is a line that is going through the circle, connected at 2 points along the circle, but not necessarily going through the center. A secant line is a line that goes through the circle that intersects at 2 points, and a tangent line is a line that goes through the circle that intersects at exactly 1 point. Okay. So, our chord-chord theorem states that if we have 2 chords that are intersecting at a specific point, and if you're looking at the definition and theorems in the book, they're going to use a lot of the same letters. So again, that's what I was saying, of try not to get confused if they look very similar. But let's call this point M for what's in the middle. And I have A, B, and we'll call it C, D. So the chord-chord theorem states that if I have 2 intersecting chords, if I take the product of those chords, so AM times BM, the product of their 2 parts that are created by the intersection, then that's going to be equal to the product of the other 2 parts of the second chord, so CM and DM. So because of that, I can find the value of missing segments as I'm going through these assignments, is the idea. In your book, and this is in the PowerPoint as well, as I scroll up here, they'll use different letters and they'll sort of highlight the different segments. And they'll talk about it in a little more detail here, but the idea is the same. The product of the 2 parts is equal to the product of the other 2 parts. So under your supplemental resources for Schoology, this is posted there where you can find it in the textbook if the 3 theorems get a little bit confusing. But that's up there in case you need it. Okay. So for this first theorem, again, knowing this relationship, I could give you the measure of 3 of these and then ask you for the measure of the 4th. So for instance, let's say I tell you that the measure, and this would be all listed out in a sense, AM is 6 centimeters, BM is 12 centimeters, say DM is 15 centimeters, and then ask you to find CM. So if I give you 3, you should be able to find the 4th using this. So just like any other thing that we've been doing with Unit 8, once I know everything except 1 missing value, I can plug it in and solve it like an algebra problem. So AM is 6 times BM is 12. That's going to be equal to CM, which is what I'm trying to solve for, times DM, which is 15. 6 times 12 is 72. CM is what I'm trying to solve for, and then I have that equal to 15. Divide by 15 on both sides. CM is equal to 72, divided by 15. And I try to give you guys answers that are integers, but they won't always be, and that's okay. This ends up being 4.8. Okay. So the length of CM is 4.8 centimeters, like so. So given the measure of 3 of those segments, you should be able to solve for the 4th, is the idea. Okay? Okay, continuing on, in the second, you have the secant-secant theorem. Okay, so the secant-secant theorem is very similar, right? It kind of looks similar. There's still line segments going through, but the chords are contained within the circle. They have endpoints along the outside of the circle. Whereas the secant line is going through it, and typically if we're talking about secants or secant and a tangent, they're going to intersect at a point outside the circle. So this one's a little bit different. So let's call this QRS, and we'll call this TVS. Okay. So with your two secants, rather than the products of the two parts being equal to each other, finding the product of the two parts equal to the product of the other two parts, here it's a little different. Here it's going to be the product of the entire line segment, in this case QS, times the segment on the outside, RS. That product is equal to the corresponding pieces of the other secant. So the whole secant, TS, times the part on the outside, VS. So same thing, if I tell you 3, you should be able to tell me the 4th. So in this example here, for secant-secant, I'd go through and say QS is 20 inches, RS is 4 inches, VS is 5 inches, find VT. So as long as I give you 3, or sorry, not VT, find, well, I could ask you to find VT, but let's say if I ask you to find TS. So you set this up, you have 20 times 4 equals TS is what you're trying to solve for, times VS, which is 5. 20 times 4 is 80, divided by 5. TS is 16. And then, of course, if you're given the inches or other unit, put the unit. So TS is 16 inches. And last, the third relationship that you're asked to know is secant-tangent theorem. So secant-tangent theorem, you're kind of borrowing the first part of your secant theorem. So we'll call this just A, B, C, D. Okay. So borrowing from the first part of the secant theorem, the whole segment, the whole secant line, AC, times the segment on the outside, AB, that's going to equal to the tangent squared. So AD quantity squared is your secant-tangent theorem. Again, if you're looking at the PowerPoint or supplementals, you may have different variables here, but the setup is the same for these three theorems. So same thing, as long as I give you two of these variables, you should be able to find the third. So let's say AC is 25, AB is 4. I want you to find AD. So you plug in what you know, 25 times 4, that's equal to AD squared. 25 times 4 is 100, so 100 equals AD squared. To solve for AD, I would take the square root on both sides, which, yes, square root has two answers, but because we're talking about length, it would just be a positive 10. Square root of 100 is 10, so this is 10. And then I didn't put any units here, which is fine. If it doesn't put units, you can put 10 units, or you can just leave it blank. So 3 examples, try to keep them separate. I would have this highlighted or written into your notes so that you have the 3 theorems, so you can identify which you're using as you're looking, because on a unit test, you're just going to have a whole bunch of circles throughout this whole segment, so you want to know what section you're looking at. That's it for today, guys. If you have any questions, please reach out to me. Otherwise, have a good day. I will talk to you soon. Bye.